All right, so let me start by first printing the head of our data set here so that we know what we are dealing with. Okay, so we have several independent variables and the dependent column that we're going to deal with. So let me bring my pen. So this this class column, right? So let me use red here. Okay, so this class is this becomes our dependent, and the whole of that. Sorry. Okay, the whole of this from variance to entropy. This becomes our independent. This becomes our independent variables. Okay, and we are going to name it as X. All right, we're going to name it as X, and this class, which is our dependent variable. All right, we're going to name this variable as Y. All right, so that's how you're going to actually divide our data set into dependent and independent. All right, and there's actually a good reason for doing this. All right, it's actually a good practice to do that. So I can actually pick everything here, which is let me do this. Yeah, I can actually pick everything here, which is the variance, the skewness, the kurtosis, the entropy. All right, so maybe I can do like this. All right, and then put comma here. Then I also pick the skewness. All right, with some comma here. Then I also pick the kurtosis. All right. Then I also pick the entropy. All right, but I mean this is only 1, 2, 3, 4. This is only 4 columns. But imagine if we have say 20 or 30 or even more. It's going to be very difficult picking them one by one like this. All right, so the best way to do is to actually just drop the part that we don't want to be present in the X. All right, so I'm going to use .drop. All right, and I want to actually drop this. I mean, it's gonna even do it just like that. I want to drop just the class. All right, I'll just drop the class, and then I will specify that what I want to drop is actually in the axis or in the column, right? It's actually in the column. Yeah. So I use axis equals 1. All right, to indicate that what I want to drop is in the column. If I use axis equals 0, it means that I'm showing that what I want to drop is in the rows, but in this case it's in the column. So I'm going to do that, and then for the Y, I'm going to actually just pick I'm just going to pick the class. All right, that's it. So we've been able to separate our data set into dependent and independent. So over here we can actually use the train test split. Remember we loaded everything. All right, we imported everything here. Okay, we imported everything here, so we can actually ignore using it. All right, if you can see over here, we can see train test split somewhere else. Yeah, you can see over here that we have it here. Okay, you can see that we have it here. So when you use the PyForest, it's actually do that for you automatically, and you don't need to actually do it again. All right, so I'm going to comment it, but that's what we are actually going to use it. I mean, we are actually going to use. So I'm not going to load it again because we've already done that. Okay, so I'm going to use xtrain, s_train. Right, and by the way, this you can easily change it and then use any variables to represent your training and testing that you want. All right, so in order for it to be easy for us to identify it, we're using xtrain and xtest, and I'm going to use ytrain. All right, and then ytest. Okay, now I'm going to use this train test. Okay, remember we import train test from this model selection. Okay, so that's what I'm actually going to use to split the data set. All right, so over here I'm going to use the X. Remember we have X which represent all these 4 columns here. All right, and then we have Y, which is representing our target. All right, then we can also split. We can specify how we want to actually split our data set. So I'm going to use test size, and in this case I want to split my data into I can use 70-30, I can use 80-20, and by the way, this is according to your own intuition. There's no golden rule to follow to use this. All right, so you can actually, this is part of the hyperparameter tuning, and you can easily tune this. If certain ratio is not working for you, you can easily change it. All right, so in this case I'm going to use let me use 20% for testing. All right, so what is actually saying here is that I will divide my data set into randomly into 80-20 ratio, right? Then I will use 80 for training. All right, for training my model. Then I will use 20. All right, I'll use 80% to train my model, and then I'll use 20% to test my model. All right, that's what it's actually going to do here, and this ratio is actually going to be done randomly. All right, it's going to be done randomly. So anytime you run the Jupyter notebook again, it's going to pick different random numbers for this. All right, so let me get rid of that. Okay, so in order for me to actually get the same random numbers when I run my Jupyter notebook, all right, when I run my code over and over again, I want to get the same random numbers being generated, and I don't want to have different random numbers. So I'm going to set a random state to actually say 1, right? This is actually also a different, I mean, is solely to you. You choose the number that you want to actually set it to, and it's just a way of controlling the different random numbers that it will be generating for you. All right, so let's run this part, and everything is fine over here. Okay, everything is fine over here. Now what's the next step? We can actually see the data point. Let me get rid of this. Let me get rid of that. Okay, now if we see the data points over here, right? If we see the data points over here, we can see that we have some to be negative, right? We have some to be negative, we have some to be 0, right? Some to be very low, all right? Some to be very low. However, we have some to be very high, right? We have others to be very high, and what is actually going to happen here is that if you're using any algorithm, we actually calculate the distance, right? The distance between each of these points. All right, the distance between each of these points. Okay, now what you have to do is actually make sure that one distance will not outweigh the other. If you remember Euclidean distance, right? If you remember Euclidean distance, it's actually saying that let me get rid of this in particular. Okay, if you remember Euclidean distance, it's saying that each point, let's say point A minus point B square plus say point C minus point D square plus, I mean up to say point M minus point N, something like that, also square. All right, so this one is actually what is going to give you the Euclidean distance. Now it's the same thing over here. If you take these numbers over here, all right, if you take these numbers over here, let's take this. So you're going to have something like 3.6. all right, let's just shorten it to 3.6 minus, all right, 3.6 minus 4.54, so 4.5, let me use it like that, squared, plus then this part 8.6. all right, you're going to have 8.6 minus 8.6, let's say 8.2. all right, so let's just run it. 8.2 squared, and then plus, let me bring this plus here. All right, plus this point, which is negative 2.8, minus, right? So let's say plus. All right, it's going to be plus 2 point. Let me get rid of that. Plus 2 point. Let me do it 5. All right, I'm writing this one. So minus is going to be plus over here, and then square plus. Then this part is going to give you minus 0.4. all right, which is this 0.4 minus this, so minus again plus 1.5. all right, squared. Okay, then 0 minus 0 squared. All right, now this is how the Euclidean distance is actually going to be calculated. Now some distances are actually going to automatically outweigh the others. If you see this part 0 minus 0, which is very less, and this part is going to be very less. However, if you take say 8.6, right, let's take the next one. Let's say 8.16 minus, after doing this, it's actually going to do the same thing for all the others. All right, it's going to do the same thing for all the others. Same thing for this, the same thing for that. So if we take, let's say 8.16 minus, so it's going to be 8.16 minus, right, minus, then minus, right, it's going to be like this, 8.16 minus, the next one is also minus, so minus 2.6, let's say like that. So it's going to be plus. So this distance is actually going to be very high, especially when you even square it. All right, and it's going to outweigh a distance on the same level, like say 0 minus say negative 3.5, right? So this one is actually going to be say 0 plus say 3.5. So this distance here is actually going to outweigh this, and it will make this distance not count. All right, so if in order to prevent this, we actually scale our data. All right, we actually scale our data so that we actually prevent this distance discrepancies. So in order to do that, we use we can use different we can use standard scalar. All right, you can use standard scalar. You can use say z-score. All right, z-score to do that. Now let's take, for instance, you're using the z-score. It's actually going to subtract the mean from each of the individual data points and divide it by the standard deviation. All right, now z-score is actually going to consider every data point in here. All right, to do this scaling. All right, it's going to the same thing with the standard scalar. It's actually going to consider every data point in here. Now if you use every data point here to do scaling, all right, before using the train test split, all right, to split your data into X train and then the X test and Y train, Y test, right? Basically to scaling before dividing your data set into training and testing. All right, it's actually a bad practice, because what we want to do is that we don't want our algorithm, all right, we don't want our algorithm to see our test data. All right, we want to train it on the training data. All right, we want to train it on the training data, but we don't want it to see our testing data. We only want it to see the training data. All right, but if you do this scaling, right, before dividing your data set into into dependent and independent, before splitting it, then it means that it's going to use this, and your algorithm is actually going to test every data point in here. All right, and later on, if you use the testing to test your algorithm is going to perform very well, right? And this is what we refer to as overfitting and data leak. All right, because just think of data leaking as an exams which maybe a question paper, right? A student has seen the question paper already, all right, and then you bring that question paper in the exam, right? It's likely that student will score as high as 90% or maybe 100%. all right, maybe 100%. But if you bring a different question altogether to this student, this student might perform very, very bad, maybe around 60%, right, or maybe 70% or something like that, all right, because it's a complete different question altogether. The same way, if your model get to test your testing data before using it to test your final model, right? If your model get to test every data point in there, all right, then your model is actually going to perform very, very well, maybe like 96% or maybe 98%, something like that, right? However, if you use this model in production and a new data set comes in, all right, if a new data set comes in, this model is going to perform very, very, very bad, like maybe around 60%, or maybe around even as low as 50%, or maybe around 70 something percent, all right, which is very, very bad, which means that your model learned too much from the underlying data that you used to train it, but it's performing very, very bad. What we want is to build a model that can actually generalize, all right, can actually work on the new data that is coming. Okay, so we want to prevent the fact that your testing data will be used in any way to build the model. All right, that's why we have to first divide our data set into dependent and independent before using training. Before using training and then testing, before dividing it into training and testing, all right, before scaling it. All right, so that's what we actually want to prevent, and that's why we're actually doing this scaling, doing this division over here into training and testing. So I have class here, all right. So we first divide it into dependent and independent before doing this training and testing over here. Okay, now after this, we can actually scale this data set. We can actually scale it so that we will not be having that distance discrepancy if our algorithm is using the Euclidean distance to do that. All right. So as I said, we can use different ways. We can use the z-score, we can use the standard scalar. All right, so in this case, I'm going to use the standard scalar, and let me see if the standard scalar is present. I'll just copy it and put it there for you so that you know what it's doing. And if it's not there, we can easily import it. All right. Okay, so I think it's not there, or maybe I'm not finding it, but let me just write it over there. All right, let me just write it over there. So from standard scalar is actually in the scikit-learn. So sklearn, from sklearn dot model oh come on, standard scalar is actually in preprocessing. It's actually in preprocessing. All right, it's in preprocessing, so we're going to import standard scalar. All right. Okay, so let's run this and see if everything is fine. Everything is okay. So now we can actually initialize it. All right, so let me just call it scalar, and then I use standard scalar. So I'm going to write the same thing here, so it's better if I can just do this. All right, just initialize it that way. Now after that, I can actually create my standardized x. All right, so if I do x here equals, I'm going to use this this variable that I've created over here. All right, so I can easily bring this here dot, then I'll just do fit. All right, then I'll transform this. I'm going to use fit transform. I'm going to use fit transform my X. All right, can do that. Or maybe the best way to do this is, let me transform this as string. All right, since I've already let me paste this here. Since I've already divided it into X string and S test, right? So it's better to do it that way. Then I'll put in here my X string that I've already have. So I'm just using this. I'm going to scale this, right? That's what I'm doing over here. And then I can also scale this as test. So I'm scaling it, and I'm storing it in the same name so that it will override it for me. All right. Dot. Then I'll use the same fit transform. All right. Fit transform as test. All right. Let me pick it again. Okay. So if I do this, let's see what happens. Transform miss S here. All right. Okay, over here. All right, so everything is fine over here. Now if I check this S string again, let me check this S string again. Okay, so now you can see that these values have been scaled, and they are all between just either -1, -2, -0. Just close to each other, unlike what we have over here, where we have some huge values and some very, very small values. So here, all right, the same way if I see the S test, all right, if I see the S test, right, the same way. And I'm not scaling the Y because remember, the Y is just zeros and ones here. All right, the Y is just zeros and ones here. So if I just show you the Y train over here, all right, it's just zeros and ones. Okay, so there's no need to actually scale that. All right, so from this we can actually start to build our algorithm. So let me just leave some space here, and then start from here, convert this to a markdown. All right, and then the first algorithm so now our data is actually ready, and we can actually perform an algorithm on it. All right, so now we did not actually use the Y test, all right, and we do not actually use that to perform the scaling. All right, so our data will not actually learn from the target, and we're going to use that in doing the testing. Okay, so those that are in Y, all right, that I want to use for testing, I store them in Y test, and those that are in X that I want to use for testing, I store them in X test, and those that are in Y that I want to use for training, I store them in Y train, and those that are in X that I want to use for testing, I store them in use them for training, I store them in X train. All right, so basically that is it, and we have scaled our data. Everything is fine. We can now start performing start building our algorithm, and we're going to start with let me do the word of this. We're going to start with logistic regression. All right. Okay. So from logistic regression, let me see if so there's one caveat when you use PyForest. All right. So logistic regression, we have the random forest regressor, we have the gradient boosting, we have gradient boosting regressor. Okay. So let me do that quickly. Let me make this thing short so that just print the head here. All right, so let me go down here and quickly start by importing the logistic regression model, right? From scikit-learn.linear model underscore model, right? You're going to import what is called the logistic regression. Alright, and one thing you also have to know that although the name is logistic regression, but we use it for classification problem. Just like in this case, we have a classification problem where we want to actually predict whether a banknote is fake or is genuine. All right. So scikit-learn.model selection, I will import this what is called the cross. What is called the cross val score. All right. Then I'll also import. So from the same sklearn, I mean from matrix, right? sklearn.matrix. Let me just do it this way. All right. Dot matrix. I'm going to import accuracy score. All right. So let me run this and see everything is fine. So let me start by initializing the classification, and I'm going to name it as classifier. All right, you can just choose any name. All right, so I'm going to initialize this. You can even choose it to be maybe your model, right? But in this case, I just want it to be classifier, so that I'll get to know it, since I'll be building different algorithms here. All right, so logistic regression, and in this case I'm going to use solver, and I'm going to use the linear. All right, so once again, all these are hyperparameters that you can be tuning to get the best accuracy score or the best performance of your model. All right, and this is going to be random. It's going to be generated randomly, so I'm using random state because just a number, which is in this case 1. All right, one thing that you can easily do is to just search this logistic regression, use the documentary, right? I mean the documentation. If you go to the documentation, you get to know what each of these parameters are, and you can easily use it. All right, so let's take, for instance, you just use a logistic regression, and you go there, and then you check for the documentation, scikit-learn.linear model. All right, so you go there. All right, you can see the various parameters that you can use over here, and the explanation of each over here. All right, the explanation of each over here. Okay, so I'm using the random state. What does it mean? You can just easily read it over here. All right, the label linear is here, you can see, and then read what does it mean. All right, so if you are not familiar with any parameter, it's easier. The documentation goes into details of what each of these is actually doing, so you can easily get it. All right, so you just read a little about that. Okay, so I'm going to use this classifier since I've initialized my logistic regression and stored it in classifier, which is going to be my model. All right, so I use classifier to learn from my data, right? So I use fit, and this is where the machine learning starts, right? So it's going to learn, right? And it's going to learn from what? It's going to learn from the X train. All right, it's going to learn from the S train. This is what I wanted to learn from, and then the Y train. All right, so this data set is what I wanted to learn from. Okay, so our model, right? This is our model, right? And we don't want it to see the testing data. We only want it to learn from the training data. All right. And then after that, I can actually use I can use this cross-val score, right? I can use this cross-val score here and get to the accuracies, all right? So let me just get it from here. And then use estimator. All right. Then for this estimator, I'm going to use that. Okay. Sorry. Then we have our x. So our x in this case is the x train which we're using over here. And then our y is the same as this. Alright, our y is the same as that. And then the CV, I'll just set it to 10. Alright, this is just the number of votes that you want. Alright, so if you see the same way as I said, if you don't get any parameter, you just search and then crossbar. Maybe let me add Python to it so that, yeah, and then you get to the documentation. All right, then you get to see all the the different parameters here. So here I'm using estimator, I'm using x, I'm using y, I'm using CV. All right, so you can easily get it, and then you see what x, what y means, what CV means. You can easily get explanation of all of those here. All right, so you just take a moment and then read about it. It's not a big deal here. All right, so moving on, you can easily do that. So after that, I'm actually going to maybe I should also print all these accuracies here. All right, so let me use print command. And then I'll name it as accuracies so that I'll get to the various accuracies after using these parameters. So all these are just hyperparameters that you can tune to get the best combinations and get the best model. All right. Then maybe we should print on the next line. All right. Then I'll print these accuracies. And then I can also print the mean of that. Okay, let me first print these. Okay, let me see what happened over here. It's supposed to just be this, which is label linear. All right, let me make sure this spelling is right. That's it. All right, so these are the various accuracies that we have. All right, these are the various accuracies after using these hyperparameters, and don't forget we are using 10 votes. All right, so we'll be having different votes and getting the accuracies for all of them, for all the 10 votes. So we can actually print the mean of this. All right, we can print the mean of this so that we have a better idea of what these accuracies are showing us. Okay, then I'll use accuracy. All right, I use accuracy dot mean. All right, so on average we have 98%. All right, on average we have 98% for this. All right, so we did it for 10 votes. All right, 10 different votes. All right, vote is just let me show you vote so that you can easily understand what this one here is doing. All right, so I say 10 votes, so maybe let's say our data set is like something like this. All right, so let me just, here we have this. All right, so we divide this into 1, 2, 3, 4, 5, 6, 7, 8, maybe 9, and then 10. All right, something like that. Now what it's going to actually do is to maybe pick this, pick that, pick that, pick that, pick that, pick that, pick that, and then maybe leave the last one, and then over here maybe pick all these, something like that, pick all these data points. All right, and then leave something like this, and then maybe here pick this, leave that, pick that. All right, pick everything here, and then maybe here it will pick here, pick like that, and then maybe skip this one. Do that, right? Do that several times. So here what it's doing is that it's going to use all these green for training, and then use this one for testing. And then use all these green for training, use this, only this for testing, use all these green for training, leaving only this for testing, leaving only this for testing. To do that, right? So this the 10 votes that we have over here. All right, and then doing that, we have different accuracies. All right, doing that and using this, we end up getting different accuracies, and then you can actually see the mean accuracy of all these. Right, you can actually see the mean accuracy of all these, and when we calculated the mean accuracy, we are getting 98%. All right, so on average we have 98%, considering the hyperparameters that we have over here. All right, considering the hyperparameters that we have over here. All right, so let me get rid of this, and then we can actually print. We can also check, maybe use the accuracy to see, to verify this. So undo. Okay, I'm going to use the accuracy score here. All right, and then I'll check the accuracy on the X test. Remember, X test is the data set that our so before we do this, we need to actually, because we will need a predicted value, so let's first make some predictions over here. So I'm going to use accuracy, maybe like that, underscore predict. Then I'll use my accuracy to predict, to make some predictions. All right, and I'm going to make the predictions on the X. All right, remember this X underscore test, this underscore test. Yeah, okay, good. Now if we see the predictions that we actually making over here, you can see that we are predicting some ones and some zeros in here. All right, we are predicting some ones and some zeros in here. Okay, so this is actually what our model is actually going to do for us. All right, so this classifier here is our model. Okay, and we are using it to make some predictions, and then we are storing the predictions in this accuracy underscore pred. All right, maybe I should do it classifier underscore that. I should actually make it like that, and then I'll print this. All right, it's actually the same thing. I'm just changing. I did not run this. I'm just changing the variable name. All right, so as we can see over here, we are making some predictions, 0, 1, some ones and some zeros. All right, and this is what our target is made of. Our target column is either we predict 0 or we predict 1, where 0 represents the banknote being fake, and 1 represents the banknote being genuine. All right, so having done that, we can actually move on to do some confusion matrix for this. All right, so for that, we're going to use this is actually imported over there, but I'm going to write it for you here so that you get to know that we are actually using this. for that purpose. All right, so let me just create a variable here. I'm going to call it CM, which is confusion matrix. I mean short form for confusion matrix, and it's just a variable that I am using, so you can use any variable name at all. All right, so matrix, remember I imported matrix here, so matrix dot confusion matrix, confusion underscore matrix. All right, then in that I'm going to use as test. I'm going to use as test, and also I'll use the prediction, I mean this. All right, then I'll set some labels here, and then the labels, we have zeros and ones. All right, we have this, and then I'll convert this into a data frame. So pd dot data frame. Okay, and in this, convert this one, the one spaces. Okay, convert this into a data frame. Now I would like to set the index, and for that I can use I for I in this, right, for I in the label. And then okay, let me do this. Good. Then I can also set the column, right? I'm setting index and columns here. I can also set the columns to let me do the same thing, and then in this case I'll use our prediction. So for I in this, instead of that I'll use this, so I'll call it predicted 0, right? So instead of just 0, I'll use predicted 0 in this case. When I print this, it will actually make sense to you in the file. All right, then I'll use predicted 1. Okay, I can even set the figure size, the figure size. So I'm going to use plt.figure. All right, so I'm using Matplotlib here, and then I'll set the figure size. In this case, I can set it to, let's just say 7 and 5. All right, and then I'm going to use what is called the heat map in Matplotlib. Then I'll pass in my, this, I'm going to pass in this. All right, then I want, okay, let me just do this and then see what I get. Yeah, you see, now it's making sense. So this is the original, right? Originally we have zeros and then we have ones here, and then we have predictions, and then predicted 0 and then predicted 1. So this one we predicted as against the original zeros and ones that are there. So let me put annotation so that we can actually see the various numbers. All right, so if I do this, yeah, now you can see that we have let me bring my pen. Now if I do this, you can see that we were able to predict 150 as 0, right? So in zeros, right, this is just 1. Let me zoom in so that you see it better. Get rid of that. Okay, so now this one is just like, it's just 1.5e plus 0.2, right? So this one is just 1.5 multiplied by 10 exponent 2. This is which is equal to like 150. All right, and the same thing for this one. This is just 1.2 times 10 exponent 2, which is like 120. All right, so now what is this one is saying is that we were able to actually predict 150 zeros, right? The zeros were 156. All right, in this case they were 156, so 150 of them we were able to predict them as 0. All right, we were able to predict them as 0. Right, however, 6 of them, right, 6 of the zeros, we wrongly predicted them as 1. Meanwhile, they were supposed to be 0, but we wrongly predicted them as 1. The same way, we're able to predict 120 of the ones as 1. All right, we're able to predict 120 of the ones as 1, while we make a mistake of predicting one of the ones as 0. All right, we made a mistake of predicting one of the ones as 0. So that's why our model is actually doing very, very good. If we check over here, we are getting around 98%. All right, that's why it's doing very, very good, because more of the time it's able to predict 0 as 0 and 1 as 1. All right, so our model is quite doing good considering logistic regression. Okay, so in the next video we're actually going to start by using support vector machine and the other various algorithms to make the other predictions. All right.